All right, this chapter is about sequences and series, and we're going to start off by talking about arithmetic sequences and series. Okay, so first let's define what is a sequence. A sequence is a list of values that follow a rule or pattern. So example, 2, 4, 6, 8, 10. We can say our pattern is to get to the next term, we're kind of adding 2 over and over again, right? Add 2, add 2, add 2. So it's following a pattern, right, or rule here. A series is if I wanted to take the numbers in a sequence and add them together to find the sum of the terms in a sequence. So if we considered each of these terms, it would be like if I wanted to add up a bunch of those numbers, we call that a series. Okay, so what makes a sequence or series arithmetic? Okay, it will look like kind of like we had here. We'll either be kind of adding or subtracting some value over and over again to get to the next term. Okay, and the value that we're adding and subtracting over and over again is called the common difference. And we use the letter D, lowercase d, to represent that common difference. The reason it's called the common difference is because its value can be found by subtracting the previous term from any term. So for instance, if I picked a term up here, let's say 6, and I subtracted the previous term from it, we would find out that their difference is positive 2. And what that tells me is that we're adding 2 over and over and over again. Okay, so you can kind of find it through subtraction. That's why it's called the common difference. Difference meaning subtraction. Now, arithmetic sequences, this is actually an important note, will look like equations of lines. These are linear equations. So they may look like, you may see them look like kind of like y equals mx plus b at some point here. Okay. Now, if we're given two random values in our sequence, like a first term and 8th term, and we want to figure out what is the common difference, because they kind of relate to equations of lines, their rate of change, or the slope, can give us that common difference. So we kind of use the slope formula. If you remember, like y2 minus y1 over x2 minus x1. This is a very similar formula we can use. So this notation we're just now getting introduced into. A sub 1 means the first term. A sub 2 means the second term, or in this case, the second value. And n's will be their positions in the list, like this is the first term, second, third, fourth, and fifth, etc. Okay, here is the formula we can use to find any term in an arithmetic sequence. So if I wanted to find, if this pattern continued and I wanted to find the 100th term, this is a formula we can use to find that. So let's talk about this notation. A sub n. Okay, A sub n means the value of the term at position n, or the value of the nth term. A sub 1 means the value of the first term. A sub 1. So this kind of subscript is kind of our position. So this is the first term. N is our position number. So if I wanted to find the 100th term, my position number would be 100. And D is the common difference. Okay, so let's try this out. Here is a pattern, 3, 8, 13, 18, 23. Find the next 3 terms of the arithmetic sequence. Well, let's figure out what we're going up or down by. Sometimes we can just kind of eyeball this. I know to go from 3 to 8, we're going up 5. So plus 5. From 8 to 13 seems like plus 5, 13 to 18 plus 5, etc. And yep, this does like we are going up by the same value. There is a common difference between all these terms. And in fact, D is positive 5. Now again, you could use the subtraction method and take 8 minus 3 to come up with 5. But if you figure out what they're adding or subtracting, that's your value of D. So don't make it harder on yourself than you need to. So it says find the next 3 terms. So if we continue this pattern, if we add 5, we would get 28. Add 5 again, 33. And add 5 again, 38. That would be the next 3 terms. Then it says find the 80th term. Now to find a term that far away, I don't want to keep adding 5 over and over again. We'd like to use our nice new formula. So if I wrote down the basic formula, the nth term equals the first term plus position minus 1 times d. So let's plug in. We want to find the 80th term. So the value of the 80th term equals, now I need to plug in the first term in our sequence, and our first term was given over here. Our first term is 3. So go ahead and plug that in, 3, plus the position we want to find. So we want to find the 80th term. We plug in 80 for n. So 80 minus 1 times d. And d is that common difference. Go ahead and use parentheses here. That does help out when d is negative, to remember that we are multiplying by that number, not subtracting. So here's our nice formula. You can, of course, follow your order of operations. You can plug this directly in a calculator as is. I'm going to go ahead and do some steps here. 80 minus 1 is 79. 79 times 5 is 395. Plus 3 is 398. The 80th term equals 398. And that makes sense. If you look at the numbers in our list, they either end with a 3 or an 8. Right? In this case, 3, 8, 3, 8, 3, etc. So it seems reasonable to me. And since it's so far out, it seems like that seems like a pretty reasonable value. Okay, so here are our formulas just for reference again. We probably don't need all the notation here, just the formula. But let's go ahead and do some more examples. Write the explicit formula, and that's this. We can also simplify this formula, as I'll show you in a second, and then find the 28th term. That's what our notation means there. So let's first write the formula, which will allow me to write any term. And to do that, all you need to write the formula for an arithmetic sequence is the first term, like what to start with, and the common difference, what to keep adding or subtracting over and over again. That's all we need. So let's go ahead and plug in the first term. We got that. The first term is negative 42. And then let's find our common difference. In this case, we're actually going down, right? We're getting larger negative values. So we'd be going left on the number line. So we're actually going down 4 each time. Now again, you could use subtraction here. Take any number, subtract the one before it, minus a negative. You do end up with negative 4. So there's D. Our common difference is negative 4. And all we needed was the first term and common difference. We can write our formula. So the value of the nth term, and we're just going to leave n as n, so we could plug in any number we want, which later we'll plug in 28, equals the first term, negative 42, so first term, plus n minus 1, so we're leaving n open here, times d, our common difference, which is negative 4. Okay, now technically, this is a valid explicit formula. However, a lot of times you will see them simplify this formula. So I'll show you how to do that. And this is where it's going to look more like an equation of a line. If we distribute our negative 4, negative 4 times n would be negative 4n. Negative 4 times negative 1 is positive 4. And now all we need to do is combine some like terms. Negative 42 and positive 4 is negative 38. But let's go ahead and write the negative 4n first, minus 38. And now you might notice this kind of looks like y equals mx plus b, right? It's kind of got our linear function. This is kind of like our y-intercept, or the 0th term. Imagine if there was a 0th term, it would be negative 38. But now you can see that this sort of looks like a linear function. In fact, it is a linear function. Okay, so here's the nice simplified one, and this is actually a little nicer to plug into. So let's use it to find our 28th term. So the value of the 28th term equals negative 4 times 28 minus 38. So we'll go ahead and plug that in our calculator. And as you can see, we end up with negative 150 for for our 28th term. And based on how my list is going there, this seems pretty reasonable. All right, let's try our next one here. Example 3. Find D, okay, that's the common difference, if the third term is 14 and the sixth term is 29. And that's what it's telling me here. So actually, remember, to find some things, I need to know the first term and the common difference. Well, the only thing I really have to relate to these things is this formula or this formula. Now, in fact, because I don't even know my first term, we can go and use this formula, treat it like the slope, okay, where the values, the difference of our values over the difference in position numbers will give me the common difference. So let's do that. Let's start with this value up top, 29. So we're following this formula here, minus the other value, 14. So we did it in this order, right? 29 minus 14. So in the bottom, we need to do position 6 minus position 3. Make sure you follow the same order there. So when we subtract these, 29 minus 14 is 15. 6 minus 3 is 3. And we go ahead and divide that out. We get our common difference is 5. They are adding 5 over and over again. If you started with a third term of 14, it went up to 29. Now there's also an alternate way you could kind of reason your way through here. If you pretended this instead was the first term, and you adjusted by moving everything, we'd have to go back to. So then you called this the fourth term. You could actually use this formula as well, plugging in your kind of pseudo or fake first term as 14. But the formula above is fine. It's slope formula, values over the position numbers. So just find the differences there. Nice, easy way to get our answer. All right, let's move that out. All right, let's find our last two here for arithmetic sequences, and then we got to get to series. Okay, find the 15th term, given that the first term is 16 and the fifth term is 28. So again, to find any term, I'd need to, to write my generic formula, I need the first term and common difference. Well, we do have the first term, but we don't know the common difference. So we can, just like we did before, find it using these 2 points. So let's find our common difference here. So we're going to subtract the values. Let's go ahead and just do the largest minus the smallest. So if we're subtracting in this order, we need to do 5 minus 1, subtract their position numbers. 28 minus 16 is 12. 5 minus 1 is 4. And now we know the common difference, what they're adding over and over again, is 3. Plus 3, plus 3, plus 3, etc. So let's write our generic formula. The nth term equals the first term. They gave us that here at 16. So again, we're following our formula here. First term plus n minus 1 times d, the common difference, which we just found out is positive 3. So let's actually go ahead and do the simplified one here. So we'll distribute 3n minus 3, and then combine our like terms. 16 minus 3 is 13. So this is 3n plus 13. So here's our nice formula, and let's use it to find the 15th term. 3 times 15 plus 13. Well, 3 times 15 is 45, plus 13 more is 58. The 15th term, if you continue that pattern, would be 58. Okay, next, fill in the gaps in the arithmetic sequence. Well, here they've just kind of written one. It looks like our values are going down, right? I went down to negative 22. We've got a bunch of blanks. And the easiest way to do this is we're going to kind of give them position numbers. Let's call this the first term. It doesn't matter if it really is or not. Let's just call it the first term. Third, fourth, fifth, and sixth terms, and then we know the seventh term. So now, like we knew up here, I know the first term is negative 4, and the seventh term is negative 22, and we can use our slope formula once again. So let's go ahead and do negative 22 minus, again, we're following the formula here, negative 4 over the position difference, 7 minus 1. So follow the same order there. Now up top, minus a negative will become plus a positive. We get negative 18. And the bottom, we get 6. And we end up getting a common difference of negative 3. So if we did this right, we should be able to subtract 3. That would give me negative 7. Subtract 3, negative 10, subtract 3, subtract 3, subtract 3, and yep, subtract 3. Perfect. It all lines up. Beautiful. All right, this brings us now to arithmetic series. Okay, an arithmetic series, again, was when we, like we talked about in the very first slide, so when I want to add up a bunch of terms. So the formula we can use, if I want to add up the first n terms, so this S stands for the sum of the first n terms of an arithmetic series, equals the number of terms divided by 2 times the first term plus, we can think of this as either the last term, or if we're adding up, say, 10 terms, this would be the 10th term. So it's the last term there. Okay, so S of n, sum of the first n terms, first term, number of terms, or you can actually think of it as the position number of the last term as well. And A sub n is either the last term or the term at position n. Okay, so a bunch of ways of thinking about that. Let's try an example here. So note, to use this formula, we need to know 3 things. How many terms, what the first term is, and what the last term is. We need to know all 3. So I've kind of created a checklist here. And if we're missing any of those pieces of information, that other formula can help me find that missing information. So let's see, for example 6, find the sum of the first 12 terms. Okay, so I actually know n. The number of terms I want to add up is 12, so we've got the number of terms. In the arithmetic series, it's good to know that this is the formula. Given the first term is 4, okay, we got the first term, beautiful, and the last term. Now again, if we're adding up 12 terms, the 12th term is the last term. So they actually did give us the last term. Perfect. We have all of our information, so we can go straight to using this nice formula. And I'll show you how this formula was derived. It's actually brilliant, but not too difficult to understand. So the sum of the first 12 terms is half the number of terms, n divided by 2, 12 divided by 2, times the first term, which they told us was 4, plus the last term, which we now know is 58. So you can just type this in as is into your calculator, or half of 12, right? It's not something we can divide nicely. This gives me 62. Is 372. If you were to add up, so if you were to generate a bunch of terms in the sequence and add them all up, your sum would be 372. Okay, let's try a few more examples here where maybe they don't give us all the information. So let's see, find the sum of the first 30 terms. So I now know n is 30. Okay, we got n. And here is, this time they've kind of given me my series. So it looks like we're starting with 4, which is the first term. Hey, we got the first term is 4. And it looks like we're going up by 3, right? Plus 3, plus 3, plus 3. That's great. But what I really need to know is the last term. They've just given me these ellipses that says it just keeps going. We don't know the 30th term. We need the 30th term. Okay, so when we're missing information, we can go back and we know a formula to generate any term we need in an arithmetic sequence or as an individual term in a series. So let's use that formula, okay, to find the 30th term. So the value of the 30th term, I'm going to go ahead and just straight plug some of these things in, equals the first term, which is 4, plus the position number minus 1. Well, the position number we want to find is 30, minus 1, times the common difference. Now, that is something I need to come up with, but I think we've actually already discovered it, right? We're going up by 3. The common difference is positive 3. So now we can generate that missing information. So we get 4 plus 87, which is 91. The 30th term, the missing information I needed, is 91. So we know our last term, we know our first term, and we know the number of terms. Perfect. Now we can use this nice Gauss formula. The sum of the first 30 terms equals half the number of terms, 30 over 2, times the first term, which is 4. I guess I could just look over here, plus our last term, which was 91. We had to go out of our way to find that, but we've got all of our information. Half of 30 is 15. 4 and 91 make 95. And we multiply those together. We get 1,425. Okay, let's try another example where maybe we don't have all the information. Find the sum of this series. Okay, well, let's see. We've got our first term. Check. That's 8. Actually, we have our last term, right? The ellipses stop here. Our last term is positive 71. This is nice. But, we don't know how many terms there are. So let's think about this. We haven't really been writing this label above them, n, which is kind of like their position number, the first, second, third, fourth. And this is the nth term. I don't know what position number it's at. So we are missing information. And again, we can use this formula to find out that missing information. So let's plug in what we do know. Okay, I do know, so in this formula, I know the first term is 8. Okay, the position number n is actually what we need. We need n, which is, again, the position number of the last term, as well as how many terms there are. So n is what we're solving for here. I don't know its value. What is my common difference? Plugging in the formula, let's see, we're going up by 7, plus 7, plus 7. So our common difference, d, is 7. Now, I don't know what n is, but I know the value of the term at n is 71. And now we have an equation with one unknown. We can solve for n. So let's go ahead and distribute. That gives me 7n, plus 7n minus 7. Combine our like terms over here. 8 minus 7 is just 1. Subtract 1. I think you can see where this is going now. 7n equals 70. So n equals 10. It's actually only the 10th term in. We now know n is 10. So we can go to our formula up here. The sum of the first 10 terms equals half the number of terms times our first term, which was 8, plus our last term, which is 71. This ends up dividing nicely, so we can do some of this by hand. 5 times 79 is 395, if I'm not mistaken. Okay, I checked. It's correct. All right, we have one last part to look at, which is a type of notation that goes along with sequences and series. In this case, actually series. Okay, this is called sigma notation. This is capital sigma, the Greek letter. And in mathematics, this capital sigma means the summation of, or to add. So if you ever see this capital sigma, that means to add, or that we need to add. So here's what we'll normally see. We'll see a number above, we'll see a little variable and a number below, and an expression in front. Kind of has a little hat, a tie, and I don't know, something in front. Okay, so here's how this. So down below, it's telling us for values of n from 1 to 10, and that means all integer values from 1 to 10. So we're going to plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 into this formula. So for instance, if you plugged in 1 in there, 2 times 1 plus 1, that'd be 2 plus 1, or 3. Okay, so when I plug 1 in for n, we get back 3. If I plug 2 in for n, we'd get 2 times 2 plus 1. That's 4 plus 1, or 5. Okay, and what it's telling me to do as I generate all these terms is to add. So if I plugged in 3, 2 times 3 is 6, plus 1 is 7. You might start to see a pattern here. It's almost like we have a rate of change of 2 Hopefully this looks like an equation of a line where our slope is 2, right? Up 2 over 1. Anyway, yes, you can see our nice pattern. It is increasing by 2 every time, so you could plug in 9 and plug in all these nice values and add them up, right? And that's what it's telling you to do with all of these values. Sigma means to add, so we'd be adding all these values up through 10. Now, because we note this looks like an equation of a line, this is an arithmetic series. And we can use that formula from Gauss, this formula, to add up all of the terms. So we don't actually need to generate every term. Remember, for this formula, I just need to know how many terms. From 1 to 10, there are exactly 10 terms. I can generate the first term by plugging 1 in my formula. We've already done that, so I'll just copy my answer here. And we can generate the last term by plugging in 10 into the formula. So 2 times 10 plus 1 gives me 20 plus 1, or 21 would be the 10th term or last term. So adding all these up, we can use our nice formula here. 3 plus 21 is 24, and 5 times 24 is 120. So if it asked you to evaluate or find the sum, our answer is 120. So let's do one more quick example here. Last one. I know this is a long video. So here it says to evaluate. Maybe try this one out on your own. See if you can follow what we just did here. Find your first term, your last term. Again, this looks like an equation of a line, so we know it's arithmetic and that we can use this formula, which is nice. So try this out, pause the video. All right, our first term that we need by plugging in 1, right? Our first value in gets me the first term. Plugging in the last value of 12 gets me the last term. And then finding the sum of these 12 terms. From 1 to 12, there are exactly 12 terms. So plugging into our nice formula, you should come up with negative 276. Okay, that's it. Sorry for the very long video. Make sure you ask questions in class, and we'll go over more examples.